Well, if probability with one variable is fun, it's now time to do probability with multiple variables. We're going to begin with what is called bivariate, which is simply two variables. So we're going to begin with a random variable x and a random variable y. If you like, think that you have a coin and a die. X is going to take on a 0 or a 1, and it represents flipping a coin, and y is going to be rolling a die, so it'll take on 1, 2, 3, 4, 5, 6. And so we can then say, let's discuss what the probability of these things happening simultaneously. So, if we have discrete probabilities like this, then we can define a joint distribution. And this joint distribution will describe to us the probability that x takes on an x value and that y takes on a y value. Now that means that the obvious events, singular events you can put in here will be the cross product of this. So we have 2, 6, that means there's 12 different things that we can ask just on the singleton side, and if we make it to inequalities, it's even more. Now, in order for it to be a joint PMF, we need the probability still to have the same rules. So the probability function has got to be less than or equal to 1, greater than or equal to 0, and the sum over all things in this possible sample space has got to be 1. And the disjoint sets will be the sum over the x's and y's in this disjoint set. All right, now, in order to have a discrete probability function, you either have to build it yourself or be given it. It's actually much easier simply to be given a distribution and ask, does it behave nicely, or how does it work? And so, let's consider the following. F of xy is simply 1/36, and this is for 1 less than or equal to x equal to y less than or equal to 6, and 2/36 for 1 less than or equal to x less than y less than or equal to 6. Now, if we don't say anything more about the sample space x and y, but we want it to be discrete, then we can observe here that it looks like x can range all the way from 1 to 6, as can y. And now, however, if you notice here, x can be the same as y, or x can be less than y. It can never be equal to y. That's what this distribution is saying. Now, we can plot these values, and I kind of like plotting these values like on a three-dimensional graph. Here's your x's, and here's your y's, and then you can put a little box column up there. And so where the x's are equal to y, and so I'm going to start at 1, 2, 1, 2, go along here. Imagine I put a little box here. Each of them will have height uniformly at 1/36. Now, when the y's are bigger than x, then they're going to be twice that height. And so all of the values behind here, I can make boxes that are twice as tall. And so here, all the way over to here, here, all the way over to here. They're all of height 236. So I don't know if you can see it. It's like a one step and then a bigger step. Or I can just take and do the x, y. Now here I got x going, y going this way. I can just put some dots, and for each dot I can put 136 here, and for each dot over here I can put 236. That's not very as pleasing, I think, as if we do it this variety. But one thing we should check out about this picture is maybe we should count, does it add up? So there are how many y's bigger than x? If x and y vary from 2 to 6, well, first off, there's 1, 2, 3, 4, 5 y's bigger than 1, 4, 3, 2, 1. So 5 plus 4 plus 3 plus 2 plus 1. Those are the y's bigger than the associated x in this picture. If I made it 5 wide, so that's 9, 10, that's 15 of those. And they all have 236. And then there are 6 that have 136. And lo and behold, that adds up to 36, 36. So that adds up to 1. All of these are greater than or equal to 0. And then we just declare that any combination of points, that the probability over that value is the sum of the individual parts. Now, it's nice when we are given a formula that maybe has a dependence on x. Now, these can be given in different ways. What's nice about them is that the formulas can be written pretty nicely. Like, for example, let's take x comma y. Is the rule x plus y over, let's say, we're doing example 4.1-2, x plus y over 21, and we then say x is 1, 2, and 3, and y is only 1 and 2. So this is a total of 6 possible pairings that go in there, and then we just have to check that indeed they add up correctly. So let's just check that. Let's put for x equal to 1. How many y's are there? There's 2. So there's 1 plus 2 is 1 plus 1 is 2 21sts. And 2 will be 3 21sts. This is for x equal to 1. So then I'll do x equal to 2. Now, again, there will only be two values. Y, 2 plus 1 will be 3 21sts, and x equals 2 will be 4 21sts. We should put a separator there. And then for x equal to 3, we have f of 3 comma y. 3 plus 1 will be 4 21sts, 5 21sts, y equals 1, y equals 2. Those are the 6 values, and again, I could make a table over here the way we did, or a columnar 3D table, but let's just check since there's 6 possibilities: 5, 4, 9, and 4 is 13, 16, 17, 18, 19, 20, 21. The sum over all of these, sum we should say, indeed equals 1. Now I want you to notice I kind of organized it here along x's and y's. What's kind of nice about that is that organization can be reflected in a fairly nice table. So I'm going to put these into a table because what I actually did is for x equal to 1, there were two values here and here. Y equals 1 and 2. For x equals 2, there were 2 values here. And for x equals 3, there were 2 values here. Now, what's kind of interesting is what we can do is we can create a vertical and horizontal sums. So if you look at this sum right here, the sum over y's for a fixed x, so the sum over y's of x of a c comma y, well, that looks like a function that depends upon your little x that you pick. So if I put a elixir there and sum over y, it looks like a function that depends on x. So let's just calculate those sums. So over here, when x equals 1, that was 5/21. And when x was equal to 2, that was 7/21. And when x was equal to 3, that was 9/21. So this thing called f sub x, where we have a fixed x, but we're summing over the y, produces a function of just x's, and it takes on 5/21, 7/21, and 9/21 for x equals 1, x equals 2, x equals 3, and lo and behold, this adds up to 21/21. This is kind of neat. These sums over the y variables produce these values actually produces a probability distribution for a given value of x over all of its possible values of y. But the same thing can be done horizontally, and we can get something called f sub y, which depends on a choice of y, and again, this time we're summing over x's, and this would take on a very different value, so we'd have to add up these three rather than those. So for y equals 1, we've got 2/21, 3/21, and 4/21, 7, 8, that's 9/21. Y equals 1, and 3, 7, 12/21 for y equals 2. Again, it adds up to 1 because it's basically they're partial sums of the complete sample space, but that looks like it's a probability function on a y value. Now, what these are formally are the following. F sub x of x is defined to be the sum over y of the f of x comma y's. So that's what I was doing here for that one. I changed x to y and y to x, rolled it over there. These are called the marginal probabilities. Of the bivariate, f of xy. Now, what's interesting is that if you start with an f of xy, which is a bivariate distribution, that means you can create an f sub x from it and an f sub y. Notice when we begin with an f, then we keep that f throughout that problem. We switch the f to a g in the same problem. Instead of putting a hat on a function, now we have to put two different subscripts on the function. Now, what is really interesting is the following, and that is, if x is independent. Now, you remember in the first test, what does statistical or probabilistic independence mean? Well, it doesn't mean that the intersection is empty. What it means is the probability of one thing happening followed by the probability of the other thing happening is just the product of these probabilities. But that makes something very interesting happen here. It says, and it's not hard to prove, that the distribution function f of xy, when it comes from a bivariate, then is equal to the f sub x of x times the f sub y of y. That's how it must occur. Now, if you have a bivariate and this property is not satisfied, then they are not independent. And, well, if this is not the case, then x and y are, well, not independent. We can say dependent. So let's just take a look at that one that we were just looking at. We had that f of x comma y, which was x plus y over 21. X varied over 3 values, y varied over 2 values. And let's just check some specific number. Just one number. So remember, it's got to work for them all. But let's check out 2, 2. Well, that's 4, 2 plus 2 over 21, that's 4 21st. But f sub x at 2, if we remember the, whoops, I got to pick it up now. We remember that columnar sum for x equals 2 here, we had 7 21st. And f sub y of 2, well, f sub y of 2 is this sum, which was 9 21st. And it's useful to note that 7 21st times 9 21st is 63 21st square. That is not 84 21st square, which says that that joint probability function that we were looking at, or the bivariate probability function, was not composed of two independent variables. They have a dependence on one another. Now, since we have this formula, why don't we see if we can come up with a formula for the f of x, f of y, and not necessarily just point-wise values, since we started with the formula, right? That seems a reasonable thing to do. So we've got f of x comma y, which is x plus y over 21. Well, what's the definition of f of x sub x? Now, x is going to vary over 3 different values, but the y is the one that we sum over, so we sum over y equals 1 and 2 of x plus y over 21. Well, that'll be x plus 1 over 21 plus x plus 2 over 21. Y is going to be 2x plus 3 over 21. And so this is for x's equal to 1, 2, and 3. Now we could have done the same thing for f sub y and summed over all 3 of the x's. We would have gotten 6 plus 3y over 21. And this would have been defined over y equals 1 and 2 only. And so given a formula, we can deduce some of these formulas. Now, I do like that these variables that we are given by formula somehow reveal the fact that these things may or may not be composed of independent variables. Most of the time, if the function itself does not look like a product function, then odds are it is not going to be the product of two f of x's and f of y's. And if you have done some things in differential equations or with certain integrals, just because something looks almost right doesn't mean it is. So if you're given a function, say like this, f of xy equals, let's say, a constant times x squared y cubed, you might think that f sub x might be some constant x squared and the f sub y is some other constant y cubed, and a times b equals c. But it doesn't by any means necessarily have to happen. It could, or it might not. It may look like it's there, but it's not. Now, when we're working with joint distributions, if we now have an f of x comma y, of course we want to mimic what we've done before. My favorite topic, of course, is that's the moment generating function. But in order to get to the moment generating function, I have to define expectations. In order to have expectations, I have to have averages and variances. And my goodness, that's kind of strange, because I want you to notice that if we start having statistics, or if this is a theoretical function, then it's parameters that describe it. on statistical values. It's like x bar is a statistic, mu is a parameter of a function. This is why we write normal mu sigma squared. These are the parameters of a theoretic function. Well, if you sample it, you may have some normal x bar s squared, and that's the best you've got. These are just estimates on an existing one. You don't know if it's actually correct. So this is why the statistics and parameters are named differently. But I would like to, from this, ask, well, does this thing have an average? And if so, what does it mean? And so very clearly, with a joint distribution, we should come up with a mechanism to calculate what would be akin to one variable descriptive statistic. So let's first just define an expectation over some function, and we'll write it as mu of this x and this y. And we'll just sum over the x and y in our sample space of the function mu of xy times the f of xy. So this looks exactly, it is a generalization of the process that we did with one variable. Now, this means that we have to do double sums, and if we're given formulas, it may be twice as complicated. But if we're getting discrete ones, they're not too bad. But what's interesting about this is that they're not really that hard to calculate in the discrete case. What's more interesting is what might happen with formulas and interpretations of what these things mean. So this is the expectation of a function. Well, within a joint distribution, one might sample this probability, and you get these pairs. One might ask, well, what's the expectation of just the x value, and what's the expectation of just the y value? In other words, it might be very useful to just put in mu of x, y, just the x variable, or the mu of x, y is just the y variable. And then this will look like the expectation of x under a joint distribution and the expectation of y under a joint distribution. So we need to have the setting done correctly so that if we know we have a joint distribution, this is going to be the mu sub x in the joint distribution and the mu sub y in the joint distribution. And so the x's and y's are happening simultaneously. Well, with that interpretation, then we can immediately, of course, move to the expectation of x minus mu sub x squared. And what is this? This will be the variance of x in our joint distribution. And the expectation of y minus mu sub y squared will be our variance in our joint distribution. But since we've got two variables here, there's something else that we can define, because I just put in a simple linear in x, namely the linear function, the expectation of x. I put a simple linear function in for mu of xy, and that was just the y. I put in a simple quadratic, x minus mu of x squared. I put in a simple quadratic, y minus mu of y squared, and these all had names. Well, obviously, there's the algebra of the linear, and you're going to immediately see, it doesn't matter if it's singular or not, a mu of xy plus b will be the xa times the expectation of the mu of xy plus the expectation of b, but that's the sum over a complete sample space, so it'll be just b. Everything behaves like it did in the original one variable sense, even though we're having two variables here. So what's missing from this list is a quadratic that's created jointly with the x's and y's. Ooh. Well, there's one that's special. It's where we use one of the x minus mu of x and one of the x minus y minus mu of y. And this is called the covariance for the x and y. It talks about how they vary jointly. Now, I bet you can guess that there's probably going to be something about independent variables that when x and y vary jointly, I bet the covariance is somehow going to be just a product, because that's kind of what it looks like. We're not there yet, but it's a very interesting question to ask. Now, at this point, we should talk about in the bivariate distributions that we'll very quickly perhaps want to be in a situation where we have more than two variables. And then we can write x, y, z, but z is traditionally in statistics and probability dealing with the z distribution in the standard normal 0, 1. So z is kind of reserved for this situation. We have a nice way to handle this. We'll start with indices. We have random variable x sub I. And that random variable x sub I, we might have it vary over 1 to 7. So I'm shaking 7 dice, or flipping 2 coins, shaking 4 dice and drawing 2 cards, and I have variables associated with them. And so we may quickly drop the x and y. We usually use the x's and y just when we're saying we have the bivariate, that we're wanting to work with just 2 things. Now, it's very, very nice to be able to look at certain distributions that, when restricted to one world or another, produce the single variable distribution. So what's interesting, if we start with some f of xy, is it possible that this can become a known single variable distribution? Well, one way to do that is to make sure that x and y are independent of each other and just multiply their 2 distributions together up here, and we can get a clearly non-dependent, but the f of x and f of y's are known single distributions multiplied together. What's more interesting is when they're not independent, yet when we do this, we can see this happen. So one of the first ones that we're going to do for this one is a really interesting one, because you've seen this structure before. So I'll start with the structure of the distribution. We start with 40 choose x. So it looks like we have 40 some things of type variable x, and x is going to vary over 0 probably to 40, or who knows, maybe 0 to 20, maybe some limited sense, we don't know. And then how about 60 choose y? So it looks like y is going to vary over something like that. But then this is going to make it much more fixed. Ooh. So now it looks like that somehow 25 things out of 100 are being accounted for here. This is the telling one. Looks like there's 100 things where it looks like there's potential for 40 of the x's, 60 of the y's, but we're only grabbing 25. So it looks like we have some strange things going on here. And now, however, I'm going to put the denominator of 200 choose 25, and let's see if this is enough to understand what's going on here. I want you to notice that 60 plus 40 is 100. This kind of looks like you're picking a total of x and y things up to 25. And so it looks like you're picking x from the 40, y from the 60 things, and what's left from the other 100. So it seems clear that we have 3 characteristics here. The x's from 40 alike things. We have the y's from 60 alike things, or indistinguishable. Isn't that the correct word? Indistinguishable. And over here, we have then from the third characteristic, a remainder to get a total of 25. But these, the remainder, come from 100. So it seems that there's like this picture. We have an urn that's got 40 of one characteristic, 60 of another characteristic, and 100 in that, and we reach in, and somehow we're describing that there are 200 25 ways to pick that out, of which it seems that we're getting at most 25 X's from the 40, at most 25 Y's from the 60, and the rest are going to be from that 100. This seems to be a perfect situation for saying, let's say, blue chips, red chips, and 9 other varieties. Let's put yellow, green, and white here. They just have to be not characteristic 1, not characteristic 2. This seems to be counting how many ways to pick a specific pairing of X and Y from an urn without replacement, because unordered is not here, 25 chips. So this looks like it's without replacement. Wow. This looks like a complicated, what do we call that? Hypergeometric. Now, what's really interesting is we need to describe these X's and Y's. And the fact of the matter is they appear not to be simply independent of each other, because if you picked 20 of the X's, then there's only 5 of the Y's left to pick from. So the increasing Y's suppress, X's suppress the Y's, increasing Y's suppress the X's. So I'm not exactly sure how this is going to be calculated without making sure that we put the right domain values in there. We just can't arbitrarily put in 20, 20, and calculate this, because then we'd have 100 choose negative 15. So we have to be very careful. So what should the correct description of our sample space be when we describe this? Well, maybe it's not worth always writing that down terribly precisely. How about we just say, well, X's and Y's are integers, and their X plus Y has got to be 25. That's all we'll say. And we'll let you guys figure it out. So this will be 0 if you've gotten 25 of the other ones, etc. Now, it's kind of unfortunate the 40 and 60 add up to 100. That kind of just misleads until you see the denominator. Now, what's interesting about this one is what happens if we decide to actually limit this. Let's calculate f sub x. Well, that's going to be the sum over the y values for each x So when you specify y equal to 0, we get our first answer. Y equal to 1, we get our second. Y equal to 2. And all the way up to y equal 25. Well, when you do that, then you get the complementary values for x equals, well, when I put in 0 then for y, then x equals 25. I put in 1 for y, then x equals 24, and it goes all the way down to when it's 25, x equals 0. So I can just reverse it. So this clearly, we know it's domain of x's. What's really interesting is that when that's calculated and simplified, it becomes the geometric distribution in x. That's kind of neat. And, sorry, not the geometric, the hypergeometric. And you know what's neat? Is the f sub y behaves the same way, except the 40 becomes 60, the 100 minus the 60, 200 minus 60 becomes 140. So these two numbers become complementary. And it's still a hypergeometric. But what's interesting here is that we've got the specific hypergeometrics that we want, but it's not the product of the two. So this distribution actually has a marginal distributions that are known to us. However, it is not the independent variables of x and y that make it happen. Now, what should we call this? Should we call this the tri-hypernomial or the it's the hyper, is there a name for it? If we do have a name for it, what should we call it? Well, it turns out that this one doesn't happen so frequently that we've named it, but I want you to read in the book about the trinomial. Remember, we've got the binomial, right? Well, there's something called the trinomial, and it happens to have a very nice formula. So that's for you to read, and it's just 1 page long. All right, there's section 4.1.